Hello everyone. Today the topic is propagation of error, which is very important in engineering design. Usually you make a measurement using some instrument or tools. For example, you measure the length by using a tape or a weight scale to measure the weight of a rock, or a voltmeter to measure volt, or a sensor to measure light intensity and sound pressure. So you have the sensor here, make measurement. Then this measurement is going to a system to process these data, and then you get an output. If there is an error in the measurement, now the error is processed and propagated to the output. And that's the topic of today. How the error in the measurement is propagating through a calculation or through a processor to the output. Usually the measurement consists of many parts, but before we discuss this part or what are the errors in the measurement, let's just take a simple example. A geologist weighs a rock on a scale and gets the following measurement. Every time you measure the weight or the volt, you will always get different values, going to be very close to each other. But the rock has an actual weight. So these different measurements, because of an error in the measurement, that error can exist in two forms: bias or random error. So the measured value will consist of three parts: the true value that you don't know, you are trying to measure, then plus a bias, plus a random variable or random error. That bias here, it's like adding to the actual weight of the rock certain gram. Every time you make the measurement, maybe 0.2 gram is added. So the system or the instrument you are using need calibration. And if the bias is always zero, we say, oh, your instrument is accurate. So bias, we call it accuracy. And this is systematic error, something we can deal with it and fix. The second part of error is the random error, the difficult one. And that random error, it just, you don't know. It could be a human error, machine error due to noise. But the error here is not consistent, like in the bias that I can eliminate. Here the random error sometimes plus 0.1, sometimes minus 0.1, sometimes plus 0.2, plus 0.15, and so forth. So it's always fluctuate plus minus certain value. And we call this random error. If that random error very small, then we say, oh, the instrument is very precise. And we call it precision or uncertainty. In medical instrument, and in many instruments, the company sometimes will send a technician to calibrate the instrument. That means to eliminate any bias. And usually, for example, they will send a fluid with a standard concentration of glucose. And let's say the laboratory equipment measure glucose in fluid. So they will give that instrument that standard fluid that they know what's the concentration, and they will make 5 measurements. X1, X2, X3 to X5. And then they find the mean of this measurement. And let's say the mean came like 30.5. And the glucose concentration, they know because they added it. So they know what is the concentration. So let's assume it is 30. Then they know there is bias that is equal half. So then they calibrate the instrument to reduce the measurement. This calibration sometimes just a variable resistor. They change the resistance by certain amount so it gives you the right output. So bias usually is easy to deal with. And how do we find the bias? As I said, you take a measurement, you find mu or x bar in this case, so that will be here, minus the true value. The true value in this case is 30. Mu here in this case is 30.5. So 0.5 will be the bias. Now the precision or the random error, you measure the fluctuation from one measurement to another measurement to a third to a fifth. Basically you are measuring the variance. And then you take the square root is standard deviation. So this variation, it tells you the precision of the instrument. And that will be the standard deviation of the 5 measurements. We can also think of the bias and random error or accuracy and uncertainty as follows. Just imagine you have a soldier with a rifle and a binocular on the rifle, and the soldier is aiming at this target here at the center, and all his shots are coming really close to this center. So we say he has high accuracy and precision. But now imagine he's using another rifle and all his shots are coming here. Now we say he has high precision because all the shots are close to each other, but poor accuracy because there is an offset. And that accuracy, this poor accuracy, may be because the binocular of the rifle is not adjusted, need to be adjusted. So that would bring this shot down to here. So in this case, with all the shot in the center, this is good accuracy and good precision. This one is good precision, poor accuracy. Now imagine something like this here. So all his shot is here. Now this is good accuracy because all centered around the goal, but they are all over, high radius. So that's poor precision, but good accuracy. A third case scenario, the shots, where it's all here. Now this is poor accuracy because it is shifted this way and up here, and poor precision because the shots are not centered or close to each other. There are too much variation between them. So that's how also you can think of accuracy or systematic error and precision, or what we call uncertainty. So let's take an example to demonstrate this concept. A laboratory sample of gas is known to have carbon monoxide concentration of 50 parts per million. A spectrometer is used to take 5 independent measurements of this concentration. The 5 measurements are this one. So we have the true value, 50 parts per million, and these are the 5 measurements. Estimate the bias and the uncertainty in a spectrophotometer measurement. The uncertainty means the precision. All right, the first step, let's find this, mu. To find the bias, I need to find mu. Mu is usually of the population, but since we don't know the population, we took 5 measurements, so mu will be estimated by the sample mean. So in this case, x bar, which is an estimate of mu, so that will be 51 plus 47 plus 53 plus 53 plus 48. Divide by 5 and you should get 50.4. So then the bias will be mu of the samples you take. So that will be 50.4, that's this one, minus the true value. And the true value is 50 parts per million. So that is 0.4. So that's the bias. So that technician can come and calibrate the instrument to reduce 0.4. So that's like a DC offset. Now to calculate the uncertainty, this one, or we call it the precision, we should find the variance. So the variance then equal the difference between each measurement and x bar, the mean, squared times the probability. So then that will be 51 minus 50.4 squared plus 47 minus 50.4 squared plus all the way to the 48 minus 50.4 squared divided by n minus 1. Here n 5 measurements, so n minus 1 is 5 minus 1. And if you calculate this, you should get 7.84. And if you find the standard deviation, it's the square root of 7.84. So that will be 2.8 part per million of carbon monoxide. And that's how we measure the bias and how we measure the precision of the instrument we are using to measure this parameter. After we measured the bias and the precision, the spectrometer has been recalibrated, so we may assume that the bias is negligible. The spectrometer is now used to measure the carbon monoxide concentration in another gas sample. The measurement is 55.1 parts per million. How should this measurement be expressed? If you are writing a document or you want to reveal this information, then you should include the precision or the random error. So you say 55.1 plus minus 2.8 per, which is this one we found. Now, we will focus from now on is on the precision because the bias is easy to deal with. We want how the precision will propagate. So for example, you may have the input here X going to an amplifier and you get Y. So there is error in X and I want to see how it propagates to Y. So X, sigma X is here. Now I want to know sigma Y, how the error propagates to the output Y. If this is just a simple amplifier with gain C, so we can express Y as Cx. So the variance of Y will be C squared, the variance of X. Now if I want to find the standard deviation of Y, then I take the square root of C, which is the absolute value of C, times the standard deviation of X. And that's how we calculate. Now in general, if you have a random variable x1, x2, xn, so in this case Y is C1 x1 plus C2 x2 plus Cn xn, and I need to find the standard deviation of Y. That will be the square root of the variance of this one plus the variance of this one and so forth, and the variance of this one. And that will be the standard deviation of the random variable Y. And this is this one here. Let's take this example. A surveyor is measuring the perimeter of a rectangular lot. He measured two adjacent sides to be 50. So let's call this side is X. Let's call this side is Y. He measured X to be 50.11 plus minus 0.05 meter. That's this one. Y is 75.21 plus minus 0.08 meter. And that is this one. These measurements are independent. And that is the case here. This is true only if x1, x2 are independent measurement. So now estimate the perimeter of the lot. So we need to estimate the perimeter and find the uncertainty in the estimate. Well, the perimeter, let's call the perimeter P, is this side plus this side. So that's 2x plus this side and this side. So that's 2y. Now to find the value of the perimeter, it will be 2 times x. So you just include this part here, 50.11 plus 2 times y, which is this one, 75.21. And if you calculate this, you should get 250.64. So that's the perimeter. Now we need to calculate the uncertainty in the estimate. So that means I need to calculate the variance of P. So the variance of P is 2 squared, so that will be 4, the variance of X, plus 2 squared, this constant, so that is 4, the variance of Y. And I can do this because X and Y, they said, are independent. So that will be 4 times, I have here the standard deviation of X, 0.05, plus 4 times 0.08. And if I calculate this, I should get 0.04. And if I want to find the standard deviation or the uncertainty in the perimeter estimation, I take the square root. And this should give you 0.19 meter. So then you write the perimeter is 250.64, which is this, plus minus the uncertainty, which is 0.19, the standard deviation of the perimeter, this one. All right, repeated measurement. The advantage of the repeated measurement is you can give a better estimate of the parameter with a smaller precision error or with a smaller random error. So you have an amplifier and you want to measure the amplification. So then you make many measurements, x2, x3, all the way to xn. And then you estimate the mean. What is the average amplification? By averaging all these parameters, x1 to xn. Then if I want to know what is the precision of this measurement of this amplifier, can I say the amplification is 10 plus minus 0.001? What is the precision of the amplification? In this case, it will be sigma x bar equal sigma over square root of n. So now when I say the average amplification of this op-amp is 10 amplification plus minus this quantity. So I would be more precise. And that's why when you make measurement, make sure you take at least 5-6 measurement to really estimate the parameter you are measuring with more precision. And we already showed earlier this relationship. We said x bar, the mean is just x1 plus the second measurement plus the nth measurement divided by n. And if I want to find the variance of x bar, it will be 1 over n, that's squared, constant, times the variance of x1 plus the variance of x2, since they are independent, plus the variance of xn. And since these all x1, x2, xn are measurement of the same device, the variation will be the same. So this is just 1 over n squared, the variance of the instrument, and there are n of them. That's 1 to n of them, so times n. So then that's the variance. Then the standard deviation, x bar, will be the square root of these. So that will be 1 over n squared times standard deviation n. This n will cancel one of these n, so then you will have the standard deviation divided by the square root of n. And that's this one here. So the more measurement, the lower your random error. Let's look at this example. The length of a component is to be measured by a process whose uncertainty is 0.05 centimeter. If 25 independent measurements are made and the average of these is used to estimate the length, what will the uncertainty be? So if you make a 25 measurement, x1, x2, all the way to x25, and that instrument that make measurement has uncertainty or standard deviation of 0.05. Now you use 25 measurement to estimate that x bar. Now they want to know what is the standard deviation, what is the uncertainty in this average of the 25 measurement. This will be 1 over square root of n, and the one is just the standard deviation of the system. So that will be 0.05 divided by the square root of 25. So that will be 0.01. So you improved the precision from 0.05 to 0.01 by a factor of 5. The cost, you made 25 measurement. That's the cost. An engineer measured the period of a pendulum in seconds to be 2 seconds plus minus 0.2 seconds. Another independent measurement is made with a more precise clock, and the result 2.2 plus 0.1. They said precise, not accurate. The average of these two measurements is 2.1. So they use the first clock and they average the 2 with the 2.2 and they got 2.1. So let's call Z equal, they average the two clock. Let's call clock X and clock Y. So that would be half X plus half Y. Now they calculate the mean of Z and they found it is half the mean of X plus half the mean of Y. So it came out 2.1. Now if we want to find the uncertainty, sigma Z will be the square root of this constant squared, so that would be 1 over 4 times the variance of X plus 1 over 4 times the variance of Y. And this is 1 over 4. The variance of X is 0.2 squared plus 1 over 4. The variance of Y is 0.1 squared. And when you calculate this, you should get 0.11 second. So the uncertainty is 0.11 second. Yes, it's still worse than this one, but better than this one. And you may say, why don't we just use this clock? Why do we have to depend on the second? Well, we don't know which one is more accurate. Yes, this clock has a better precision, but I'm not sure about the accuracy. It could be this is more accurate. So we just take the average. And by doing the average, we reduced the uncertainty to 0.11 second. Now, another engineer may come and say, since Y is more precise than X, a weighted average in which Y is weighted more heavily than X might be more precise than the unweighted average. instead of using equal average, why don't we just say z equal cx plus 1 minus cy? So that's unweighted average. Here C could be 0.2. Here 1 minus 0.2 is 0.8. So I'm estimating Z by taking 20% of the value of X and 80% of the value of Y. Unweighted average. This is just an example. The question is, express the uncertainty in terms of C and find the value of C that minimize the uncertainty. So now we need to find what should be C. Should it be 0.2, 0.4, 0.1, 0.5 like here? That will minimize the uncertainty. That will minimize sigma Z. So I want to minimize this. So what should C be? First, we have to express sigma Z in terms of C. Then to find the minimum, we take the derivative of sigma Z with respect to C and set it to equal 0 and then solve for C. Just like calculus, when you try to find the max or the min, you take the derivative and you set it to 0, then you solve for the parameter that will maximize or minimize. Okay, so now let's express sigma Z in terms of this equation. So then let's do the variance first. So the variance of Z square equal C square times the variance of X plus 1 minus C square times the variance of Y. And I can do that, I can sum this way because the clock, X clock and the Y clock are independent the way they operate. They are not affecting each other. So that's the variance. Now I need to find C that will minimize this quantity. So to do that, let's take the derivative of the variance of Z with respect to C because that's the parameter I can change. So C is a variable. I can change the value to be 0.2, 0.4, 0.8. I cannot change sigma X. I cannot change sigma Y. This came with the design of the clock. All I can change is the weighted average. So then I will take the derivative of sigma Z with respect to C that I can change. So that will be 2C sigma X. That's a fixed. I cannot. So you can think of it as a constant plus 2 times 1 minus C time the derivative of inside. So that's minus 1. I use the chain rule. Time the constant. That's sigma Y squared. So this is 2C sigma X squared minus 2 sigma Y squared plus 2C sigma Y squared. Now to find the value of C that will minimize this quantity, I set this derivative to a 0 because if I plot this and I get this one, then the minimum will be here, the slope will be 0. So if I set that to 0, then this will be, let's gather all the 2C, so that will be 2C sigma X squared plus sigma Y squared minus 2 sigma Y squared. And then I solve for C. And C in this case will be 2 sigma Y squared over 2 sigma X squared plus sigma Y squared. And this finally equals sigma Y squared over sigma X squared plus sigma Y squared. And that's exactly what this slide all about. If you have X and Y are independent measurement with uncertainty sigma X and sigma Y, then the weighted average, which is this, will give you the minimum uncertainty if you choose C to meet this condition, which is this one, what we just found here. Remember, in this case, C best is in front of X, so that is sigma Y. 1 minus C best is sigma X squared. The denominator is the same, just the average. So if you choose the weighted average this way, then you will minimize the uncertainty in the average of X and Y. So let's go back to this example. We have a clock X. The uncertainty of a clock X, sigma X is 0.2 and sigma Y 0.1. So in this case, the best value for C, the weighted average that minimizes the uncertainty, is the variance of Y squared, 0.1 squared, divided by the variance of X, so that's 0.2 squared plus 0.1 squared. and this value should be 0.2. So the best average then 0.2x plus 1 minus 0.2 is 0.8y. And in this case, 0.2 times x is 2 plus 0.8 and y is 2.2. So the pendulum, the clock, the average will be 2.64. And the uncertainty in this case will be square root of C1 squared, so that's 0.2 squared, times the variance of x, which is 0.2 squared, plus c squared here, which is 0.8 squared, times the variance of y, which is the square of 0.1. And this will be 0.008, and that will be 0.089. And I can approximate it just 0.09. And this is the standard deviation of z. So the standard deviation of z, now it's better than 0.1 and the uncertainty of clock y, which is 0.1, and the uncertainty of clock 2, which is 0.2. So now I can say the mean is 2.64 plus minus 0.09. So far we were talking about x and y. If I add them up, linear relationship, they are independent. But what if x1, x2, xn, this measurement are not dependent? But it's still linear relationship. It's still like z c1 x1 plus c2 x2. So it's still linear relationship plus cn xn. But now you cannot assume they are independent. So we cannot use a formula like this. So then a better estimation, even though it will be overestimating, it will be the standard deviation of z will equal or less than C1, the absolute value of C1, times the standard deviation of x1, plus C2 times the standard deviation of x2, plus Cn times the standard deviation of xn. You use this one if you don't know if x1, x2, xn are independent, then use this. If they say they are independent, then the standard deviation will be the square root of C1 squared, the variance of x1, plus C2, the variance of x2 squared, plus Cn squared times the variance of xn squared. This is for independent, this is for dependent, so you do overestimation of the standard deviation. So a simple problem like this, a surveyor is measuring the perimeter of a rectangular lot. He measured two adjacent sides to be 50.11 plus minus 0.05, and the other one is 75.21 plus minus 0.08. And find the conservative estimate of the uncertainty in the perimeter. So the perimeter is 2x plus 2y. So the uncertainty in the perimeter will be equal or less the constant, the absolute value, times the standard deviation of x plus 2 absolute value times the standard deviation of y. So that will be 2 times 0.05 plus 2 times 0.08, and that will be 0.26 meter. So that is an estimation. Because we don't know if x and y are independent. We don't know if they are independent. So we overestimate. We solved this problem earlier, but was mentioned that x and y are independent. And the standard deviation of the perimeter must be less than this. So let's double check. Yes, here. And they said the measurement are independent. And we find the uncertainty 0.19, which is less than this uncertainty 0.26. Okay, so make sure when you solve the problem, are they independent or not? Thank you for watching and see you next video.